I'm Thomas Bonnier. I'm from the Center for Ice and Climate in Copenhagen, and I talk about paleoclimate, specifically about ice cores. And the period I'm going to cover is the last 800,000 years, where you have detailed information. It's a pleasure for me to be here and to talk about paleoclimate. This is the first part of two talks. The second talk will be by Valérie Masson-Delmotte after the break. We have not talked together, so you might see some of the slides I show in her talk as well. And you will see some of the slides that Thomas presented in my talk, because all that I do and did, and all that ice cores are doing, is part of the IPCC report. And you will find this in chapter 6 if you search for it. So I thought I'd start a little bit about me, but Carlo already did that. Then I give a short wrap-up of the greenhouse effect. Then talk about ice coring, show a few pictures that you know what we are talking about. Talk about the recent atmosphere, the last 1,000 years, and then the distant past, glacial interglacial changes going back 800,000 years into the past, and then shortly about rapid climate change, all in the paleo perspective. As Carlo said, I'm coming out of the lab where that Thomas Docker is heading now. When I started, it was headed by Hans Oeschger, who is a famous climatologist. He actually is the name giver of one of the medals here at EGU. The medal lecture for that is this afternoon at 1:30, but of course you're busy. And I moved to Copenhagen and still do ice cores, and specifically I do trace gases. This is a picture of me if you don't recognize me in the field. And when I'm not in the field, this is my lab. This is how a lab looks like for trace gas analysis. Has a lot of tiny tubes, gas bottles, mass spectrometers, gas chromatographs, things like that. Just to remind you what the atmosphere is composed of, most of it is nitrogen, we have 20% oxygen, and then the anthropogenic greenhouse gases, carbon dioxide, methane, and nitrous oxide, and you have this here in ppm, parts per million in the dry atmosphere. This is the status 2011, which is the breakpoint for the IPCC report. 390 ppm for CO2, we just made it over 400 this year. Methane is 1.8 ppm, and nitrous oxide is about 300 ppb. Greenhouse effect, when we look at our planet as a black body, then we have an equilibrium temperature that can be easily calculated by this equation here, and we get about 7 degrees Celsius. Anybody knows what the average temperature is today? It's on the order of 15 degrees. So we're quite a bit off, but not that much. Now, when we include that about 30% of the incoming radiation is thrown right back into space, we get a much colder temperature. We get about minus 17 degrees. And only by putting in the atmosphere, you have the incoming radiation seen from looking up from the Earth, and the outgoing long-wave radiation looked at from space, we are getting the right temperature, which is 15 degrees Celsius on average. So it is really important that we do have an atmosphere and we do have a greenhouse effect. Otherwise, we probably wouldn't be here. Now, the radiation is not evenly distributed over the planet. It's actually pretty inconvenient how it comes in. Most of it comes in on an annual average over the tropics, and higher latitudes, like here above 40 degrees, would probably be pretty inhabitable. So a major component of the climate system is that heat is transported. And it's transported over the water cycle and over the gases. Now, what is I think it's quite a fascinating way to look at it. Is this popular representation here? This artist here, he has pulled together the whole ocean and put that into a small sphere, and the whole atmosphere at sea level pressure, and you see how little that actually is. And these two small square balls here, they are a major component of the climate system. They decide how the energy that comes into the planet is redistributed. And I'll get back to that versus the end of my talk. So here's a very long-term perspective of the climate system. We're looking at the last 70 million years. This is a temperature record that mostly comes from benthic foraminifera in the ocean. Don't mind the scales. Important thing is that we are basically going downwards towards a colder state. What is marked on this graph is that the point, well, first of all, we start out at in a very warm situation in a greenhouse where there's no permanent ice on the planet. And only about 35 million years before present, we start having sort of a permanent Antarctic ice sheet. And then it still goes a long way till about 2.7 actually million years before present, when the Greenland ice sheet is forming, so that we have ice on both poles. How we get from here to here, that's a complicated story. It certainly involves CO2, but it also involves other components like the position of the continents. Now I'm only bringing this up because we are looking at exactly these two places. We're looking at Antarctica and we're looking at Greenland. That's where you can drill ice cores. So here is the places where you can look for climate archives in ice. Greenland, so this here is sea ice, not really matters for us. Greenland and Antarctica. And then there are a few other places like low latitude glaciers in Switzerland, for example, where you also can drill for a little bit of ice core, which are not as long as the ones, or as far-reaching back as the ones from the two poles. How much ice is actually in these ice sheets? It's a huge amount. So when you look at all the glaciers and you would melt that and put it right into the ocean, you get a sea level rise of something like 0.5 meter, ballpark. Greenland is about 6.5 meters, and Antarctica is huge, about 73 meters. In total, we have about 80 meters of sea level if we would throw all this ice into the ocean and melt it. So here's a sketch of an ice sheet, the Greenland ice sheet specifically. We have a zone where we have accumulation of snow, and then you have a zone of ablation where the ice is melting. And those two zones, they are connected by these flow lines where the ice is flowing from the accumulation zone into the ablation zone. Now in the middle of the ice sheet, the ice is basically just flowing downwards. And here you see how far back in years we get when you get further down. The layers get smaller and smaller. So we have about down to half the depth of the ice sheet. We have about 10,000 years. And we reach something like 120,000 years in the Greenland ice sheet. This is about 3 kilometers. So when you stand on top of the ice sheet, you have 3 kilometers of ice below you. I understand there are some people from the US here. So my colleague, Richard Alley, has written a popular book. It's called The 2-Mile Time Machine, and 2 miles is pretty much 3 kilometers. So 10,000 years, that's also how far back our present warm period is going. So here you see a climate record, and pretty much half down the record we have the present warm period, and then we go into the glacial period. Now in Antarctica we reach much further back in time, and that is because the accumulation is much lower in Antarctica. So there we go back something like 800,000 years before present. And that's the time period where you have the best climate information from paleo records. The ice core archive, that's actually more than one. And that is what makes ice core so special. We have information which is in the precipitation water itself, and I expect that Valerie will talk a lot about this. I will also use it, of course. It's one of the principal components that we have from the ice cores. Then you have whatever is trapped in the ice, from chemical components to dust to tephra layers. And then, that's my specialty, we have small air bubbles. And those small air bubbles, they come from the atmosphere. As I said, one of the most important records from the ice cores is coming from the water itself. And water has different isotopes, O16, O18, and the abundance is quite different. So there's a lot of O16, but not so much of O18. And the important thing is that this is a temperature proxy. Proxy is something that stands for something else. So we are looking at information that represents the temperature of the precipitation. Now, proxies are sometimes a little bit tricky, so there's not a one-to-one relationship between this parameter here, which is the deviation of this ratio relative to a standard. It can be a little bit more complicated. Another example for a proxy is like you can look out of the window and look at how many people are walking around in t-shirts. And from that, you can conclude how warm it is outside. Now, that information or that relation between people outside wearing t-shirts and temperature can be a little bit more complicated. Just assume that you have more or less wind, which you don't see looking out of the window. So the temperature might be pretty warm, but it's pretty windy, and therefore people are not wearing t-shirts. And that is one of the complications that you also have with all the proxy records that exist. We have pretty much figured this one out for the O18 of the water isotopes. Okay, further, we have all the chemical information. We are measuring up to about 10 species of chemical components in the ice. And this gives us various information about different parts of the climate system. I'm not going to talk further about this because my specialty, as I said before, is trace gases. What you see here is an extraction of gas from the ice. It looks like it's boiling, but that's not what it is. You look closely, you see that here we have, this is the ice core, piece of the ice core. You have tiny air bubbles. This outer cylinder here has water, but this water is about room temperature. All it does is it heats up the inner part here of the ice, and these tiny air bubbles, they explode in a vacuum in this vessel here. So, talking a little bit about ice coring and showing you a few pictures on how this is done. This is from a project that we finished in 2012. It's called the NEAM project. Ice coring is pretty expensive, and you have lots of collaborators. There are 14 collaborators in that project. It has been led by Denmark. We reached bedrock at this place here called NEAM, 77 degrees north at 2,537 meters below the surface. Here's how we get up there. Kangerlussuaq is the international airport of Greenland, and then we fly along the coast and then inland to the place called NEAM. And we do that with these Hercules transporters. That's the 109th US National Air Guard, who has skis on their planes, luckily. And we can use those to get onto the ice sheet. This is a putting crew of one of the field seasons. This is when the plane is then landing on the ice sheet. As I said before, Now we have 2.5 kilometers of ice below us. Building of the camp, most of the science and the drilling is done below grounds. So we make these trenches here, then cover them up with wood and cover them again up with snow. And that's where most of the science is happening, and the drilling. This is the main dome, still in construction here. When it's finished, it will be nice and black. That's where we have a kitchen, we have toilets, showers, and also a place where you can work. The drill, not exactly the drill that we have been using here, but they all go along the same principle. We have here the drill head, 3 cutters. The core will then be here in the inner part. The chips are transported up here and are brought to the surface. You have a battery pack, and then you have this part here, which locks the drill in the hole. The drill is not like drilling for oil. This is a drill that is on a cable. And that means we have to hinder that the drill turns when we start drilling. So these blades here, they cut into the sides of the borehole and they hold the drill. Here's how this looks in reality. Drill has gotten a little bit bigger. So with that thing, we can drill up to 5 meters of ice core in one go. It's lying here horizontally. When we drill, it's tilted and then let down into the borehole. That's when the core comes out of the drill and is stored till it's further processed by an armada of students, which we bring into the field. So we do resampling for the 14 nations, and we pack them individually and we send them out. This is one of the teams. We also do science in the field. So we measure on this tiny, about 3 by 3 centimeter stick of ice. We are measuring a lot of chemical components already in the field, and we also started measuring gases with these analyzers here, which are laser analyzers, spectrometers in the field. Yeah, this starts, and then we get out of the field again, which can be a little bit tricky when it gets warm in the summer, which happens. So it can get close to 0 degrees at this place. The snow gets sticky, and it gets a little bit more difficult for the planes to take off. And that's why these planes, they have solid rockets on the side, and then you see the firing of those in this place. And it's also a little bit of a dirty thing. Right now. So we don't like doing that at all, but sometimes it's necessary. Okay, so how does the gas get into the ice? This is a sketch of the first roughly 100 meters of the ice sheet, and this zone is an open porous material. It's actually quite surprising that you can go to some depth and there are still pores. So what happens here is that in the first few centimeters, the snow is, by diffusion, forming spheres. And then these spheres are reorganizing themselves until they get the closest packing. The closest packing they reach at the density of about 550 kilos per cubic meter. And then the ice actually, or the still firn it's actually called, starts to deform until it's ice, and that happens somewhere between 60 and 110 meters below the surface. And only there the gas is actually occluded in the ice. Here you have a cut through the ice at various depths, and you see that at 10 meters you can pretty much just walk through this piece of ice. When you go further down, it becomes more difficult. This is, of course, a two-dimensional picture, so in 3 dimensions you can go much further even. And only about at 70 meters you have these individual, well enclosed gas pieces. Now the consequence of that is also that we can, other thing. First, so that's when we have gas bubbles. They look like that. And here is a plot that shows you the number of these bubbles per cubic centimeters with depth. And of course, we first start squeezing them together till we reach a maximum. And then the number of bubbles is actually going down till we have no bubbles at all. So all the gas that we trapped at the surface is disappearing. So where is it going? Is it eaten up, or what happens? What happens is that the gas is going into another form. It's going into clathrates. Clathrates are cages formed by water molecules, and the gas here, that's a methane, is sitting right in the middle. This structure is much smaller than the gas bubbles, and these structures then cluster together like that. And when you look at these gas hydrates, they start increasing when the number of gas bubbles is going down. So the gas is still there, it's not going away. It just takes another form. So the gas is occluded in 70 meters. It goes through a porous layer. This porous layer is a static air column. That means that already going down this hole, we find gas which is quite a bit older than what we find at the atmosphere. But it's not occluded in the ice yet. And here's how we probe that. We have a tube that goes down. So first we drill a hole, then we put this tube down, inflate it, seal the hole, and then collect gas from down here. The reason I'm telling you that is that we have to make sure that what we are measuring in the ice core is really what we have from the atmosphere. So there's an intermediate step. We have the atmosphere, then we have the firn, which is still gas, not occluded in the ice, and then we have the ice core. What you see here is the last 1,000 years from ice cores in the beginning of the record here. Then we go over to firn record here, and then we have direct atmospheric measurements. And you see that they match perfectly. So there's absolutely no doubt that what we are measuring from the ice core is really what the past atmosphere has been. CO2, up to something like 1850, we have a pretty constant concentration. Then we start rising. CH4 shows the same pattern. N2O is exactly the same. And world population is increasing too, so it of course hints that this has something to do with us. Let's talk about CO2 a little bit. This is a graph from the IPCC. There are very nice graphs in there, which shows where the carbon is sitting and how the carbon is exchanging in the different reservoirs. So in terms of the atmosphere, here we have the atmosphere, and you have huge exchange fluxes that go into the biosphere here and back. And of course, we have the contribution from us, from the fossil fuel. You've seen that curve before. It's one of the most famous curves that we have. It's the Mauna Loa curve that shows the increase of CO2 over time. And when you look, there is in detail, there is an annual signal on this thing. The red is the northern hemispheric signal, blue is the southern hemispheric signal, and black is an average. We have these oscillations because of the biosphere. As I said, we have huge exchange fluxes. They come with the annual cycle. They come with photosynthesis and respiration. So in the spring, the plants are taking up CO2. In the fall, they're releasing CO2 into the atmosphere again. And that's what we see here. And when you look at this formula here, there is a correspondence between CO2 and O2. And here is the O2 record. And you see that we have also an annual cycle in the O2 record. Of course, it's much smaller because we have much more O2 in the atmosphere than we have CO2. But on a mole-to-mole basis, you would expect that for each mole carbon that is either released or taken up, we will see exactly the same signal in O2. The increase, of course, is not due to the biosphere, but due to the burning of fossil fuel, which also results in pulling down oxygen and increasing CO2. Now, when you make this calculation here, you find out that there's not a one-to-one correspondence. We are missing CO2, and this CO2 is going into the ocean. And information that we can get from the ice cores is also the isotopes, and the isotopes are telling us something about where this carbon is coming from. You have the increase in CO2 here, and that corresponds to a decrease in C13 in CO2. When we put carbon from the biosphere, fossil fuel, into the atmosphere, that has a signature, an isotopic signature of something like -25 per mil. And that explains why, starting out at something like 6.3 per mil, we are getting lighter over time when we put carbon dioxide into the atmosphere from the fossil reservoir. Okay, a little bit about methane. And here's coming one of the big methane producers. It's ruminants, cows. Here is where it's coming from in detail. A lot of the additional CH4 that is put into the atmosphere is coming from fossil fuel. And then we have things which are related to food production, like the ruminants and rice agriculture. And that explains the increase of methane from the pre-anthropogenic concentration. You see that in recent years we had a decrease of the increase, starting something like in the 1990s. And this is probably related to Russia, who started plugging some holes in their pipes of gas production, or actually shut down production plants totally. We see in recent years a increasing contribution, and we are still speculating where exactly this is coming from. So finally, I see that I'm getting a little short of time here, to the long ice core records. For that we have to turn to Antarctica. This is a picture of drowning mudland, and that is a time this is a picture from the time when the ice core was drilled. At that time, this research unit here was built. It is in operation now. It has nothing to do with the ice coring at all. So, 800,000 years of ice core records. This is now deuterium, which is the same as the oxygen record. It's a temperature proxy. Here you have the last 10,000 years, going back into the glacial, interglacial, glacial, interglacial, and so on. So this has been going on for a while. Glacial means that we are putting water from the ocean on the continent. And we can see that in the isotopic signature of the ocean water itself, basically. And we can translate that into a sea level change. Now here is a scale that gives you the approximate sea level change that we observe in previous glacials, and you see that the sea level is something like 120 meters below what it is today during a glacial period. When you make a frequency analysis of these records, there are three frequencies that show up: 100,000, 40,000, 20,000. And those frequencies, they correspond to the frequencies that we observe on Earth's path around the Sun. It is the eccentricity, it is the obliquity, the tilt of the Earth axis, and it is the precession of the equinox, the position the spring point is at a certain time. When you calculate how much change in energy those changes here correspond to, it is tiny. It doesn't explain anything on the glacial interglacial changes that we see. There are huge feedback mechanisms that are in there that can then get the planet into a glacial state. Okay, this is just a picture which I was hoping would start. Or a simulation of how the ice sheet is shrinking at the end of a glacial period. So it starts again. You see that all North America or all Northern Europe is covered by ice sheets, corresponding to about 120 meters of sea level. There are changes which are in the biosphere. This is a last glacial representation of the biosphere. This is how it looks today. So you see a much more green than before. So all these places here, as I said before, they're covered by ice sheets, so there can not be any vegetation. But also when you look further down here, these are not forests. This is more like something like savanna. Changes in global temperature all over. And when we look at the trace gases now, we have temperature in the bottom, we have CO2, we have CH4. You see that there is a very good correspondence between these records. So basically there's a one-to-one relationship between temperature, the CO2, and the methane record. So comparing glacial to today, the global temperature has changed about 3 to 8 degrees Celsius. We have these huge amounts of ice which are sitting on the continents. Sea level is about 120 meters lower. We have a massive reduction of vegetation, and the CO2 is about 30% lower in the glacial than it is in the interglacial. How to explain that? You can explain the glacial interglacial changes by about 50% due to greenhouse gases and about 50% by changes in albedo. Greenhouse gases, you see two that you usually don't see very much. One is water vapor, the other is CO2. Water vapor is a passive component of the climate system. You cannot change the water vapor content. The water vapor is a slave of the temperature itself. CO2 is a different story. The important thing here is that you cannot explain glacial interglacial changes without taking CO2 into account. CO2 is important for that change. It's fundamental. Then you have 50% albedo changes which explain the rest. We have ice sheets which are reflecting more. We have sea ice cover which is bigger, which reflects more. We have vegetation that changes. Different vegetations have different albedos. And we have the clouds that make change. Thomas has shown this before for CO2. This is putting the climate record into context to the recent increase. And as he said, there is no analog for the present situation in the last 800,000 years. And I believe that is a time period that matters to us because we are in a climate system which is close to what we have now, with glacial interglacial changes, but nothing like millions of years ago. What is true for CO2 is also true for CH4. It's an even bigger increase compared to what nature is doing by itself. Now, I'm already over time, but I still want to talk a little bit about this time period here, which is the last 80,000 years. We have more information about this time period because we also have the northern hemispheric counterpart of the record in Antarctica. That's what you see here. On top you have Greenland, below you have Antarctica, and in between you have the CH4 record and the CO2 record here. Now, what springs to the eye is that we are in the glacial period here, but in that glacial we have changes which are quite significant. We have these oscillations here, and these oscillations, they are quite short, they're quite abrupt. So we are looking at changes which are happening on a decadal scale. The duration of these events is a few centuries to maybe 1,000 years. Now, when you think back of what I told you before, the orbital frequencies, they are absolutely not important for those changes here. This is something different. Now, in Antarctica, you also see oscillations, and let me pull up a few lines here. These oscillations are not as abrupt as what we observe in the northern hemisphere. They're about as frequent as what we observe in the northern hemisphere. Methane is showing pretty much exactly what the Greenland record is telling us here. And methane is not originating from Greenland. It's from somewhere else. And this methane here comes from somewhere in the tropics. So it shows that these variations here, they're of some extent. Actually, they're pretty much all over in the climate system, except for Antarctica. How to explain that? Here's a way. It is heat exchange. It is heat exchange between the southern hemisphere and the northern hemisphere. And here's one option. It goes over the ocean circulation. It goes over the thermohaline circulation that starts out here in Greenland and then is able to transport heat down to Antarctica and up again. Now, this has been termed the bipolar seesaw. Here's the first attempt to get that to work, which didn't really work. And it also implies that when something is happening on one hemisphere, it happens exactly counterpart in the other hemisphere, which is not exactly what we observe. We observe something which is more complicated, where we have a slow increase in the southern hemisphere. Not much happens in the northern hemisphere, and then we have this jump in the northern hemisphere. And at that point, we start decreasing the temperature in the northern hemisphere as well, and it also goes down in the southern hemisphere, and it also goes down in the northern hemisphere. So here is another idea, which actually comes from Thomas. It's a concept, and the seesaw has an add-on, and this add-on is a buffer, and this buffer is the Southern Ocean. And by doing that, it can be explained how we see this pattern between the southern and the northern hemisphere. But the important thing is that we are looking at the redistribution of heat in the climate system. And that means that even without forcing from outside, we can have a change in the climate system. But of course, it has to be balanced. When we see an increase in one place, we need to see a decrease in another place. And that is a process which, of course, can be on top of the climate changes that we see. So, from my point of view, there are a lot of uncertainties in the climate system, even by applying all the nice models that we have. There are uncertainties and things which can happen. Okay, by that, I think I want to change. I'm already over time. And I thank you for your attention, and I'm ready to take questions.